Next up on stage is Jan van der Vecht. He has about 3.5 years of experience at a major airline as a data scientist. But he recently switched to the dark side, to data engineering. And he actually founded his own startup called Cubonacci, where they are working on a machine learning lifecycle management platform. He will today talk about dynamically generating schemas from arbitrary objects. So please give a round of applause to Jan.
Yeah, thank you, Max. I'm very happy that all of you are here. And it's nice, I think, a nice sequential talk to what Matej talked about with MLflow, because we're in a very similar space. Before I'll introduce myself, I'll quickly go over what we're going to talk about. First, I'm going to talk a bit about the context on why we're solving this technical problem. So I'm not, for that, I'll talk 3-4 minutes about the product that we're building, because it's relevant for why we actually solve this. Then I'll explain the problem and I'll go over the solution. And afterwards, if we have enough time, I'll talk a little bit about what additional benefits you get for once you actually solve this problem. So, my name is Jan van der Vecht. I worked at KLM for 3.5 years as a data scientist, where I focused on a lot of different machine learning problems. And over time, like in the progression of my career there, I get more and more like frustrated with how difficult it was to get these models to production. So I spent more and more effort on thinking about engineering, how to do it from a technical perspective, how to do it from a more cultural or organizational perspective. And the last 9 months, well, as Matej mentioned already, we also worked on an internal platform that would help data scientists to get more autonomy in getting their models to production and reducing the time to market and making it more robust. After those 9 months, I decided to quit my job and start a company that's in a bit of a similar space, and that's called Kubinashi. So Kubinashi, as it says here, it's a machine learning lifecycle management platform, which is a fancy word for doing all the plumbing around machine learning models. But we've done it from a very heavy philosophy about how that should be done. Given my own background, which is more of mathematical background, and having worked as a data scientist for quite a while, we've really focused on the user experience of the data scientist so that he or she doesn't have to do things too much differently from how they're already used to in their Jupyter Notebook or in their PyCharm, whatever. While still having a lot of the things afterwards leveraged or abstracted away. Our focus is a bit wider than MLflow. So Git, like CI/CD part is part of the deal, but also like scheduled retraining, the monitoring part, etc., is part of it. So as I mentioned, Git is part of it. This Git repository of our users follow basically a certain structure. We have a very similar idea as MLflow that you should be very flexible. So you want to use your own tools that you're used to or want to have the option to try very different things. So that's why our basically the customizable part is code-based. So if you want to use, at the moment our focus is Python, our support is coming soon. So if you want to use scikit-learn, TensorFlow, PyTorch, or your own custom algorithms, as long as you basically implement certain interfaces in your code, you can connect to our system. So that basically the main components are the model definition, the metrics, so you can define your own custom metrics as code, so to closely align to your business objectives, and a data loader, which is basically some kind of interface to your data. We also don't do the data versioning ourselves because it's a very difficult topic to generalize, but this data loader is the part I'm going to talk about today. Our platform runs on Kubernetes, which means it is installable in any Kubernetes cluster, which is usually the cloud environment of our customers. So the part that is where this is the first part where this is important is you can deploy your model as an API, which includes the monitoring part. And we are interested in the schema of your data, but you don't specify some reference to your data or where can we find it, but you actually supply some code that retrieves that data, either in memory or you can copy raw code somewhere and then pass a generator or a TensorFlow data, for example, back that we will use to pass to your model. here's a really quick example where this will load your training data. And the reason why we do this as code is to be flexible, but also so that we can repeatedly call this code to get new data snapshots so that we can actually do scheduled retraining of your models. In this case, as you can see here, this is a kind of a scikit-learn approach where you pass back two Python objects. And because I mentioned we don't want to give the feeling to our potential users that they will be restricted in how they solve it, these Python objects can be fairly arbitrary. In this case, it's a pandas data frame. It's very easy to extract a schema from it because you just look at the D-types, but we also want to support a list of nested dictionaries, for example. So that's what my talk is going to be about. So how can we basically take an object from our users and kind of learn what kind of schema it has, which will then allow us to do all kinds of nice things, and we don't have to inconvenience our users by having to pass schemas to us. You can still do it, by the way, but it's not necessary yet. So the challenge is we have some objects, so that could be features, this could be targets, this could be predictions generated by your model, this could be feedback that you retrieve later for the monitoring part. And this object can contain all kinds of things. So it's basically, it has to be some kind of list or iterable or indexable object where every row represents a sample. But it could be text-based, it could be arrays or matrices, it could be images, time series-based data. And here's an example of something like this one sample that our users' code could pass to us. So here, this is a dictionary. It has a profile element, which is another dictionary. There's a purchases, which is a list of strings in this case. And it's a photo, which is a three-dimensional, sorry, which is a three-dimensional NumPy array. So we have this sequence of samples. These samples can be nested. They can have missing values. They could be of different types. They could be variable length. And the goal is that we can look at a lot of these samples and still have some like schema definition as the output. So the solution is kind of two parts. First, we want to infer a schema for a single sample. So this example that we saw, we're looking for a method that takes this as an input and produces some kind of schema. So this function, that is the first part of the solution. These schemas could be basically split up in two types. So you have primitives, which is basically the unit object, or this base thing that you cannot split up further. Some kind of atomic primitive, which could be integers, floats, strings. And you have these composite schemas that can be basically have children again, or references to other schemas. As an example, are lists, NumPy arrays, or dictionaries. So these primitives are pretty easy. We first will just take a look, like, is this part of data, or this part of this Python object, one of our known types, so one of our supported primitives? If so, we can pass a schema object, or schema, yeah, an instance, which has this primitive type in it, and there could be some metadata involved. And you can just do this with, there's a lot of more specialized ones, but the most famous ones are instance of and type to kind of check, like, hey, is this an int? So here, one would map to this int, to the string, or to the float. These composite types is where it gets more interesting. We could have these lists, these number arrays, or the dictionaries. And for every of these supported primitives or supported composite types, we have a custom schema class which contains some metadata or references to others. So these, a lot of these have children, which could be primitives themselves or composites themselves, and the relationship, how these are related. So now I'll give two examples that will showcase this part a little bit. So first we have a NumPy array, which is a composite because it consists of multiple things. And in the metadata is basically the shape. So the shape basically explains what is the size of this NumPy array. And then as a child, there's, in most cases, it's just a primitive D type, which could be int32 or these kind of things. In theory, you could have you have structured NumPy arrays as well, but we'll leave these out of the talk for now. And another case that is actually pretty common is dictionaries. And you would say, like, why do you want to support dictionaries? Well, in my experience, a lot of more managed services basically force you to use either just tabular data, or they could be images or things like that. But in my experience, I really like working with kind of custom models. So there's a lot of multimodal cases where you would want to combine images with text or time series together with some static metadata. And being able to express that in a natural way, I think is important to be able to support as many use cases as possible. Of course, there's other ways than just passing dictionaries, but this is a way to allow this flexibility. So with a dictionary, the metadata is the keys, so basically the references to all the different parts or the different values in the dictionary. And the children are basically, for each key, this is a schema that corresponds to this key. So that could be, if you have a age, then the key is the age, and the child is this primitive schema of an integer. But these could also be composites again, which basically leads to this recursive relationship where you can have basically unlimited nesting. I'll give a quick example of the dictionary that we saw before. So here we have the profile with the age and the province. We have these purchases, which includes the number of purchases, which might be a case at Zalando. And then here's the photo, which is this three-dimensional NumPy array. So we map this individual sample into a schema that looks like this, where we have this dictionary schema. Inside there's the key profile, which is another dictionary. This purchase is a list of strings, and this photo is a NumPy array. Now that we've kind of defined how to do this first initial step, where we can take a single sample and try to deduce some kind of schema out of this, we could do this for all the samples in our set, or maybe a sample of these samples, but that depends a little bit on how varied these can be. And the goal is then to take all these different schemas, so these different structures, and merge them into one schema that is basically defining your whole data set. So an example here would be, we have this is a smaller version of the previous one. We have a dictionary with an age, which is an integer, and this list of strings, which represent the purchases. If we then have a different schema from a different, deduced from a different dictionary, which doesn't have these purchases, we have some kind of merge conflict, I guess. And we're looking to basically combine these, but saying that it's like the first one is not correct because there's a different sample that looks differently. So another a way to actually merge these together would be to define these purchases as a like optional list of strings. So there's a lot of ways how you can basically find these conflicts and still learn something that says something about both of them. A use case of this is then later, if you're missing an age and all your samples in your training set had this age, it's not a maybe, so it's not nullable. You could throw an error like, hey, this is not validated. But in the case of these purchases, you could see that in your training set or in where you deduce these schemas, this was commonly missing, or maybe just once, but at least it was missing, so then this is acceptable. The nice thing about this is that it's these kind of two steps. They fit very well in a common way of dealing with larger sets of data. Because first we take these samples, and each of them we map to this corresponding like schema object. Afterwards, we reduce these multiple schemas into a single schema, and we end up with a schema that defines how our training set looks like. A really nice thing about this is that it's very easy to parallelize. For example, with Spark, you can do this. So where we have a list of these samples, we map them to the schemas, and then we reduce, like continuously reduce pairs of schemas into a final schema that we can then use everywhere throughout our product. So one of the one of the things that we can then do, the first basically interaction with it, is that we basically automatically create these dynamic API contracts that are then used for model deployment. So then you can think about basically the JSON representing this nested schema, and we can basically use that to turn your model class that we train on and automatically deploy it. So in that sense, it's similar to MLflow, but in our case, our interface is the Python code or the Python interface that you implement instead of some API contract that is shared. And we can also do that for very clear error handling. So if something is wrong, we can say, hey, this key in this dictionary was not missing during training, but is missing here, to make it easier to take care of that error handling. And something we're working on now is where we train our own anomaly detection models on your data. And to be able to do that, we use basically autoencoders and deep learning. The structure in your code or the structure in your data, we can use that to basically determine the structure of the neural network that needs to be done. And later, that's not really in our scope, but AutoML things could also be useful because then we can have different models that can deal with this maybe weird structures. As I mentioned before, there's kind of this nice feature of approaching it like this, is that we use it now for determining all kinds of types and these structures and these types, but you actually get a lot of additional benefits because these kind of map-reduce paradigm that we're already using for the schemas can be used to generate all kinds of statistics as well that could be useful for describing maybe automatically, automatically describing it in our user interface to more business applications or automatically document things. But also for automatically deducting that something, even though the schema is correct, it falls outside of the range of the data that we've seen before. There's a lot of nice streaming algorithms that fit very well in the MapReduce part, which includes this min, max, the means, counting the number of missing values, and there's even a really nice streaming variance algorithm that fits in this. I went a bit fast through this, but I want to thank you for your time, and you can find me here on LinkedIn, or you can send me an email. Thank you.